Swayam Prabha. Digital India. Educated India.
Now I won't give the expressions for, so I here have given expressions for the TM mode. I expect you to do the same analysis for the TE mode yourself, okay? There you will find a similar treatment, except that for this figure where we have E perpendicular to this H plane, there we'll have, I beg your pardon, for the TM mode we have H perpendicular to the E plane. For the TE mode, we will have E perpendicular to the H plane. Okay. Please do the TE mode analysis yourself. Okay.
So is there any bouncing plane wave phenomena going on in the TM parallel, like TM mode for parallel plate waveguide mode?
No, there is no bouncing. It's just that multiple waves exist.
Okay.
When I say TE mode, it is a wave. It is one electromagnetic wave. When I say TE mode, it is another electromagnetic wave. If I say that a parallel plate waveguide has solutions for all three, that is TEM, TE, and TN, it means all three types of waves coexist and they transmit together. That's what it means.
So the power transmission is a result of all the three modes existing inside the waveguide.
So these are not theoretical concepts, these are actual waves. You can filter out one from the other.
Sir, is there any dominant of TEM, TE or TM? Is there any dominant mode that which exists in the?
I'll come to that in a moment. Okay, so in summary, yeah, please.
So how do we decide that N? In the TM mode, there is that AN and sin N and phi Y.
Good question. So here you see that there is this small n term. What does this mean actually? Now this n is any integer starting with 1. So if n is any integer starting with 1, then that means for each value of n we will have a different solution for Ez and Hx, right? And which is true. Which basically means that for the TM mode, you don't have a single solution, or physically speaking, you don't have a single wave. So if you consider even the TM modes, it means that there are multiple TM waves coexisting together. Is that clear? And these are, when I say modes, these mean individual waves. You can filter out these waves. You can, for example, you can have one going in one way, other going in different way. Now,
sir, one doubt I have.
Yeah.
In when you are speaking about TEM wave, then you took the transverse field, like when the direction of propagation is along z, then you took Ex and Ey, Hx and Hy.
Right.
And when you are talking about the TM mode, you have taken the non-transverse components also.
Yeah, because the shape is like that. The wave shape is like that.
Means what I'm asking you is the same footing for TEM and TM modes. Like for TEM you took the transverse component, and for TM you have taken the non-transverse component. Like suppose TM you have Hz is 0, but Ez is not 0. But Ez is not a transverse component. Only Ex and Ey are the transverse component.
Let's see this figure. Is this figure visible?
Yes, sir. Yes.
This is the TM mode. Here, E, see, when I have concentric circles, it means E has both. So my coordinate system is like this. See, H is only along Y, but E has components along Z and X.
Yes, sir.
Is it clear?
Yes, yes.
Did I answer your question?
No, sir. What I'm asking is like, sir, for TEM wave propagation, since EZ is 0, HZ is 0, you took the components as EX and EXEY and HXHY. You said because those are non-zero,
I
you
took
took
means
those.
I got it from the solution for the parallel plate waveguide. So the
Yes, sir.
parallel plate waveguide is placed like this.
What I'm asking, sir, is in TM mode, transverse magnetic mode, where HZ is 0 and EZ is not equal to 0.
Right.
So even when EZ is not equal to 0, do we need to confine only to the transverse field EXEY,
No, if
HXHY, or we
EZ
need
is not equal to 0, it is TE mode. It is not TM mode. You
Okay.
cannot have both EZ and HZ not equal to 0.
Okay.
Is it clear?
Okay.
Is it clear?
Yes, sir.
So are
Yeah,
those
please.
concentric circles of the electric field that you are considering?
This I've drawn it as a concentric circle, but it's more like an ellipse actually. It's an ellipse.
Okay.
In fact, in Posar, in the book by Posar, you can see for a rectangular waveguide, they have given the diagrams of the various modes. You can have a look at them. Now, one other point, since he mentioned the n, that for various values of n, I can have different TM mode solutions, right? That is evident from this equation, right? And each of these modes are given a name like TM1, TM2, TM3. Now, a rule of thumb is that the number of subscripts, see here it is like only one subscript, right? But when we consider a rectangular waveguide, we will see that we have modes like this. When we consider a dielectric resonator antenna or dielectric resonator waveguide, we have modes of this fashion. So the rule of thumb is that the number of degrees of freedom that you have in your waveguide will determine how many subscripts you have. We cannot have more than 3 spatial degrees of freedom, so we cannot have more than 3 subscripts. Okay. So for a parallel plate waveguide, where the only degree of freedom that you have, if I go back to my parallel plate waveguide, see, for the parallel plate waveguide, the only freedom that I have is changing the distance between the plates, 1 degree of freedom. That's why I have only 1 subscript. But when we consider a rectangular waveguide, we write the subscript in this fashion. Okay. Now coming to a rectangular waveguide, so far we were discussing a parallel plate waveguide.
So what is the difference between guide wavelength and normal operating wavelength? You have mentioned the lambda G
Yes.
guide wavelength. So what is exactly this guide wavelength?
Yes. Good question. So, okay, let me draw it fresh once again. Say this is my parallel plate waveguide. Please excuse my handwriting. I just cannot do it better than this. Okay, let me try to draw it properly.
Sir, I had a small question.
Yeah.
So in the ends will be limited, right? Like the Kc has to be smaller than K, otherwise it will become an exponentially dying out wave, right?
Yes. Yes. Yeah, absolutely.
Thank you.
Sir, and one more thing, like the ends can, like we can't take it that beta can go as close to 0 as possible, right? Because that beta should still be above the cutoff frequency.
Yes,
So only till that value of n we can actually tolerate these
yes,
waves.
yes, yes, absolutely. So yeah, so I'm trying to position my whiteboard properly. So this is my parallel plate waveguide. Say this is my electromagnetic wave in free space. I'm just rubbing these things out, okay, so this is my electromagnetic wave in free space, which I introduce into this parallel plate waveguide. When the electromagnetic wave was in free space, okay, in free space, wavelength is lambda, say. Now, after entering this waveguide, if I consider the TM mode, the shape of my wave becomes like this. Okay? Is this clear? Is this clear? A student had asked me, what is the difference between lambda G and lambda? Yeah, so is this clear? So after it entered the waveguide, its shape changed. Okay, now it is shaped like this. This is for, of course, only for the TM mode. Okay. Now for the TM mode, this is the shape. For the TEM mode in free space, this is the shape. This is a different wave. This is a different wave from this. And it has a different lambda, which I call lambda G, as compared to this. Is it clear now?
Sir,
Yes.
so how does this transition from free space to concentric circles of E take place?
It takes place because if power is to transmit through this waveguide, then this is the way if power is to be transmitted through this waveguide in the TM mode, then this is the shape it has to take as
Why?
per Maxwell, because if it has to conform to Maxwell's laws.
Okay.
Is it clear?
Yes, sir.
If it is converted to the TEM mode, then it will still continue to be a plane wave.
So how is it decided whether it will convert to TM or TEM mode?
That depends on the transition, how we introduce it. So something that I have not given here is, between a plane wave or a source, suppose you have some signal generator, okay, say, which is generating the frequency. Now, how you connect that to this? So when you feed from your signal generator, say it is through a coaxial cable. Now, in a coaxial cable, the mode is TEM. Okay.
Yes.
So if you say connect it appropriately so that only the TEM mode in the coaxial cable is later on converted to the TEM mode of this parallel plate conductor, then there will only be TEM. But if you suitably engineer the transition between the coaxial cable and the parallel plate waveguide, so that before entering the parallel plate waveguide, the wave is already converted to a TM or TE, then most of the power will be transmitted as TM or TE. Is it clear?
Yes, sir.
So once a wave is entering a waveguide, can we generally assume that it will take up all possible forms of TEM, TE, and TM?
No, it depends
Without
on
any
how you
filtering?
feed it, how you are feeding it.
Okay.
See, it's all depends on, you have to go into the details, how exactly you are feeding say, as I said, if you're feeding using your function generators, the function generators that you're familiar in your analog lab, then from the function generator, you have a BNC cable, right? And BNC cable is a coaxial cable where the dominant mode is TEM. So that's what I said. I mean, say you connect it the way you are connecting the BNC cable to this parallel plate waveguide, and such a way that all the TEM modes are that in such a way that the TEM mode is never converted to TE or TM, then TEM mode will be the maximum component of the transmission. Is it clear?
Yes, sir.
In fact, at one point in this course, we will discuss about transitions, about how you can convert one mode to another mode. For example, in a rectangular waveguide, which we will discuss next, that it's a single conductor waveguide, so there is no TEM mode, right? There is only TE or TM modes. Let me.
Sir, how do we decide if it is a rectangular, then TEM does not propagate, only TE and TM propagates?
Because rectangular is a single conductor waveguide.
Okay.
Whereas, as you saw, for the parallel plate, there are more than one conductors, right?
So then in case of parallel plate waveguide, we need to have the surface current distribution picture, and then we need to understand how many modes are, getting propagated.
Can you please repeat the question?
Like, for example, we have designed a parallel plate waveguide and we want to verify the number of modes or the dominant modes or the combination of modes that is getting propagated.
You want to see what modes are actually there, right?
Yes. So how will we do that? Like, will we find out the...
There is no single answer for that. It depends on how you're feeding it. As I said, if you are feeding in such a way that you are only allowing, it's all the engineering, like for example, say for rectangular waveguides, there is a method, by which we feed from the side like this. Suppose, so rectangular waveguide, just to repeat, it's a hollow pipe, it's not a solid pipe, okay? It's a hollow pipe. And you are feeding a coaxial cable at the sides, say. You have to design this properly. We shall see how to do that. That the waves, it's not that there is a fixed way that this percentage of the power will be transmitted by as TEM, this percentage as TM, and this percentage as TE. It all depends on how you are engineering it, how you are connecting your cable to your waveguide. There is a lot of engineering here. There is a transition here. Now this transition, every component will have to obey Maxwell's laws. Okay. Now, if this component, this transition or this interface between the rectangular waveguide and the coaxial cable is designed in such a way that only TM modes are allowed, then the bulk of the power will be transmitted as TM. If this transition is designed in such a way, and by design I mean the shape, such a way that only TE modes are allowed, then the bulk of the power will be transmitted as TE mode. It's all, yeah.
During the design, like when we simulate, so what do we need to keep on visualizing? The current distribution, like with each combination of our design, like when we are optimizing. When
you're simulating on a software, is that the question?
Yes, like before we are fabricating.
In a simulator, you have, in a simulator, say you are using CST Microwave Studio, or sorry, not CST, HFSS. In HFSS, you can specify that at the beginning, at a starting point, anywhere in the waveguide, the wave that is going there is TM mode.
Okay, so we will decide it.
You can decide that you can decide that, say at this point, the wave that is being introduced on this waveguide is the TM mode. So you don't need to worry how the TM mode reached at this point.
Okay.
But when you are actually, say in a lab, when you're working, you have to have some source, right? Some function generator, signal generator, where the power is usually transmitted through a coaxial cable. Yes. In a coaxial cable, the main component is TEM. So if you say have a coaxial cable here and you want to transmit TE mode here, then you'll have to think about how you will create this interface so that this TEM mode is ultimately converted to TE mode. So that is a problem that you as a designer will have to decide.
So that should be solved during the simulation phase, because in the practical phase, how will we verify that whether TM is getting generated at all? Like, verifying, testing whether actually we are getting TM as per our design or not.
Okay, so since I'll just show you how it is done. Suppose you have a waveguide. Okay, this is a waveguide. This we will discuss later, but since you have raised this question, I will just show you how it is done. This is our waveguide. Okay, this is the side view of our waveguide, and this is our coaxial cable. Is it visible?
Yes,
now
sir.
in a coaxial cable, since it is TEM mode, the electric field is radial and the magnetic field is concentric. Fine. So magnetic field is like this. Okay. When I connect my coaxial cable on the side like this, what happens is the magnetic field has the same sense. It just is transmitted like this. And my electric field, which was radial, slowly becomes like this. So ultimately what you have is a TE wave. Did you understand this figure?
Sir,
Yes.
It's a bit hazy.
sir, I'm just you are saying that probe feeding in waveguide. You mean to say?
Okay, let me draw. Yes, probe feeding, coaxial. Let me try to draw. Yes.
Yeah, it means you want to say that through a drum kind of shape, which will used to excite a waveguide for like different mode, dominant probe feeding basically.
This is what is known as a TEM to TE. TE mode converter. So this is my coaxial. Okay. Fine. This is my coaxial. In a coaxial, my electric fields are radial. Okay, but magnetic fields are concentric. Right? So I have connected my coaxial cable to the side, not at the end of this rectangular waveguide. Fine?
Oh, fine, sir.
Now, when I connect like this, what happens is this magnetic field maintains the same sense like this. And my electric field, the red line, becomes like this. So net result is that finally you have electric field like this and magnetic field like this. Okay. Now what mode is this? This one.
It's a
Which mode is
So the
this?
figure is
TM.
not synchronized.
Yeah. TM.
TE.
Okay, fine. You are making electric lines vertical. Okay, fine.
So you see, that's what I was talking about the engineering. Because I connected my coaxial cable this way, I could convert my TEM wave in the coaxial cable to TE. Now, if you want to transmit mostly through TM, then you'll have to think about it. How to convert this TEM to TM. That is you as an engineer. So this is something that some engineer has thought, that how to transmit power from a coaxial cable to a rectangular waveguide. He came up with this solution. But if you want, say, to convert from TEM to TEM, TEM to TM, then you have to think of the way how to do it. Is this clear?
Yeah. Okay. Okay.
So this is, that's why I cannot give you an answer. So in this case, the bulk of the power will be transmitted as TE mode. TM modes will be suppressed because the way I have designed this transition, my bulk of the power will be transmitted as TE mode. So the question that you were asking, that how means what percentage of power will be transmitted as TEM, TM, TE? I cannot answer that. It all depends on the engineering. How you connected, how you interfaced your source to your waveguide. Is that clear?
Yes, sir.
Do you want me to continue or should I end the class? Okay, fine. Okay, bye.